Hello, my name is Nacho Giraldez and I am an artificial intelligence scientist. Welcome to the basic deep learning implementation tutorial. This is a quick coding tutorial intended for a target audience of people who have a basic knowledge of deep learning principles and want to get up to speed on how to quickly implement neural networks using standard tools like Keras, Tensorflow. So let's get down right into it. Let me open my IDE, which is PyCharm. Here we are going to create a new Python file. Let's call this file, for instance, tf for TensorFlow starter.py. Okay. In our program we will have two different parts, but first I am going to switch to presentation mode. Okay, much better now. We will have this initial part in which we will put all the declarations of the constants that we need. Let's call this declaration part, so that the data is separated from this other part of our program that we are going to call the program body. So it is always a good idea to start by printing on the console the version of the TensorFlow library that we are using, since they tend to vary from one version to another. So we might do something like this, in lowercase of course, print f using TensorFlow version. Now we can put the version here, something like tf for TensorFlow and then underscore version underscore. Then before I forget, I will import TensorFlow as tf. Of course, I am assuming that you have previously installed the TensorFlow library. And now we are ready to go into the first part of our program, which is going to be the loading of the dataset. In this quick tutorial, the dataset is a classification problem in cybersecurity analytics. So every packet that travels through the computer network is assigned certain values according to the Cisco NetFlow standard, which defines up to 200, more than 200 variables of metadata for every packet. And then every packet has been labeled as either an attempt of intrusion or a legitimate traffic packet. So first of all, I am going to read the data set into a pandas data frame. So let's call the data frame raw data. Then I will be using pandas read CSV function to read the CSV data set into the data frame. let's use a constant for the data path, which I will have to declare here. So in my case, the data path is going to be something like a home nacho BP and then transformed dataset .csv. Okay, of course this will be different in your installation. I forgot the double quotes of the string. Okay, now we have double quotes. Before I forget, I am going to import a couple of things. Number one, I will be using later NumPy that I will import as NP as usual. Then I will import pandas as PD. Okay. So now that I have read the data set into the data frame, it is always a good idea to check the shape of what has been read. For that we can print f loaded, and then we can print out the shape. So we would put raw data, then the shape. Okay, now we have our data set loaded into a pandas data frame. So next part would be to split. So we will be splitting into training and test set. Split. Before doing that, I am going to create two different views. One, uppercase X, that will contain the descriptive attributes. So it will be something like raw data. Then I will use iloc, and I will select all rows and all columns except for the last one. And then I will create a separate view for the target values. So I have to select all rows and only the last column, which in my data set contains the target value. And then I am to perform the actual split into training and testing. So I will end up with xtrain, the descriptive attributes of the training set, then xtest, descriptive attributes of the test set, ytrain, target values for the train set, and then ytest, target values for the test set. And I will be using a scikit-learn function which is called train test split. So the parameters will be the x view, the y view. We have to select a test size. I will put this test size into a constant. We can name this constant, for instance, split ratio. Okay. And then it is always a good idea to shuffle the data set so that the ordering of the rows in your original dataset does not play any role here. Okay, and before I forget, I will define in the declaration part the split ratio, which can be, let's say, 25%, which would correspond to 0.25. You can play with different split ratios here. 0.25 is reasonable. Now that we have split the data set, we can start defining the topology of the neural network. So let's put here define topology . Okay, so we are going to use as front end the Keras API, and we will be using as back end Tensorflow. So for the front end we have several options for Keras. I will be using the simplest Keras API, which is the Sequential API. So my topology will be a feed-forward topology, which is the simplest for a neural network. So this will be my feed-forward model or network. And as I said, I will be using Keras Sequential. Before I forget, I am going to import. So let me write here import, no, from TensorFlow import Keras. Import Keras. Okay, now I am ready to continue down here. Okay, so next I am going to define the topology of the neural network layer by layer. So my first hidden layer will be a full connectivity layer, which in Keras is called dense. And let's put here 32 artificial neurons. You can play with different numbers here and see how the learning capacity changes. Next, we have to specify the kernel initializer. So this indicates from what distribution the initialization weights will be taken. So let's put this as a constant, something like weight initialization distribution. And before I forget, I will define something for this in the declaration part. So let's make weight init dist. Let's put something simple like the normal distribution, for instance. But this has to go in lowercase. Now, normal distribution. Okay. Let me go back to where I was. Kernel initializer. Now, since this is the first hidden layer, we need to let Keras somehow know the amount of inputs that this first hidden layer can expect. So we do it with the input shape, and we define the shape of the input tensor. So again, I am going to use another constant input size. Since my data set has one dimension, I don't need to specify anything for the second dimension. Before going on, and before I forget, I am going to define this constant input size. Okay, so in the case of this cybersecurity analytics dataset, there are 70 variables, descriptive attributes. So now I have the input size ready. So next would be to specify the activation function, in lowercase of course, to specify the activation function of the neurons. So we are going to use hyperbolic tangent. So TF NN hyperbolic tangent. This is a reasonable choice since the target values are +1 and -1, which are the extremes of the range of hyperbolic tangent, and hyperbolic tangent has an S shape so that it has saturation parts and linear parts. So this seems a priori very convenient for this problem. After this first hidden layer, let's add an additional hidden layer after this one. Again, this is going to be fully connected or dense. We can put here, let's say, 16 artificial neurons, and the rest is pretty much the same. So we can copy and then paste. I don't have to specify the input shape because Keras assumes that the output shape of the first hidden layer corresponds with the input shape of the second hidden layer. So what comes out of a layer is the input for the next one. And then let's write a final layer. Keras layers, again dense. Now this is going to be the last one, so we'll put here a single neuron which will provide the output, and okay, again I can copy and paste since I want, for simplicity, the same kernel initializer and the same activation function. Okay, and the topology is now ready. I think I forgot something here. I have just seen it, and S is missing here. So it is always a good idea to check that the topology is properly defined. So a way to do this would be to print the summary of the model. So we would do something like this: print feed forward model, and then the method summary. Okay, So this will print out to the console the topology that we have just defined, and it will indicate the amount of weights per layer and overall amount of trainable parameters. Okay, so next step would be to, let's write it here, configure the machine learning algorithm. Configure the machine learning algorithm, the training algorithm. Okay. So we are going to use something simple like stochastic gradient descent. So let's call our algorithm MySGD, standing for stochastic gradient descent, and we will be using the definition, the standard definition in Keras. So TF Keras optimizers SGD. Then we are going to configure our optimizer. First we have to provide a value for the learning rate. Again, we are going to put this into a constant, the learning rate. So let's go up here. Okay, and give a value to our learning rate, which is going to be 0.01. Okay, and now we can continue with the configuration of our machine learning algorithm. Next, we are going to specify the weight decay constant. So weights that are not used or updated frequently will be going towards 0, decaying towards 0. So for decay constant, decay, again I will put this into a constant, let's call it weight decay, and now I will define up here this weight decay constant. We want the weights to decay rather slowly, so let's use something like 1e minus 6, for instance. Okay. Going back to the configuration of the SGD, the next part would be to specify the momentum constant. Let's call this momentum, and then let's put something like 0.9. The momentum is going to help get closer to a minimum in a faster way. Optionally, you can use a sophistication of the basic momentum algorithm. which is called the nested of momentum, but this is optional. But it has been shown to improve the convergence in many problems. But as I said, this is optional. And now we have already configured our machine learning algorithm or optimizer. Now we are ready to compile this. So in our network, which is feed-forward model, we will compile with these parameters. So the optimizer is going to be the one we have just prepared, and the loss function, we can use something like mean absolute error. And the metrics to be reported, let's put this one as well. By the way, we can put only MAE for brevity. Okay, so now we have our machine learning model configured and also compiled. Okay, so the next part would be to proceed with the training. So before we proceed to training, if the data set is unbalanced, like this data set is, because as you guess, most of the traffic in a network are not intrusions, attempts. So most of the records in the data set correspond to legitimate traffic. So the data set is very much unbalanced towards the majority class of legitimate traffic, being the intrusion detection attempts the minority class. So since the data set is very much unbalanced, it is always a good idea to try to give it a balanced treatment so that the majority class doesn't dominate the classification metrics. So one thing we can do is to compute class weights in a way that balance both classes. So a quick way to do this would be to compute the unique values of the target variables. So we will put them into a list, unique Y list. For that, it is very convenient to use NumPy unique. And we can give it, for instance, Y-train, the target values of the training set. And then let's put that into a list. Okay. Now we have the unique target values into a list. Now we can compute the class weights that are required to balance the classes, and we will put them into an array. So we can again use scikit-learn, class weight. Before moving on and before I forget, let me import this up here. So we would write from sklearn utils import class weight. Okay, before we forget. So now we can go back to where we were. Okay, we have class weight, and now we are going to compute the class weights. We want the computation to output a balanced data set, so we specify that we want it balanced. And then the next parameter will be the list of unique target values, which is this one. And then the training set, the target values of the training set. Okay. So this will compute the class weights required to provide the balanced treatment to the unbalanced data set. So we need to put them into a dictionary. So let's do something like this, class weights dictionary, and let's store them into a dictionary. This is the dict constructor. Then zip is very convenient for this because solves the problem very quickly. And we have the unique white list. Okay. And then the class weights we have just computed, but we are going to need to have them into a list, so let's put them into a list. Okay. Yes. So it is always a good idea after doing this to print them on the console to check that everything went smoothly as expected. So we would put something like F using automatic class weights for class balance. Okay, and now we can print out the class weights dictionary. This one, yes. Okay. Okay, so now that we have the class weights that we need, we are ready to train our feed-forward model. So we will provide a training set. First, the training instances that we stored in xtrain. Yes. Then the target values for those instances, which are stored in ytrain. Then we have to decide on a batch size. So let's put this into a constant. After this amount of instances have been processed, then the gradient will be updated. So we can go here. I see I forgot something here. The weight decay, yes. So for the batch size we can use, let's say 25 or 50. Batch size equals 50, which means that after 50 instances have been processed, then the gradient is computed and the weights are updated. Okay, that's the batch size. Then the amount of epochs that we want, you usually will want a large number here, a large integer number. Again, let's put this into a constant that we will call epochs. Let's move up and put some value here. For instance, the amount of epochs, maybe a very large integer number, so it is always a good idea to use the NumPy integer 64 data type. And you will want to put here a rather big number usually, but we can start with something small. You can later increment this. So, okay, so finally we only have to specify the class weights that we have put into the dictionary. Yes, okay. So this would execute the training of the network with the topology that we specified and the algorithm that we configured. So next you will want to evaluate the network. So for doing that, we can print a message here so that it is clear that the execution has moved on from training to evaluation. In order to make this more clear, you can add a new line. And we want to evaluate on the test set, of course, so we will obtain the test loss and the test accuracy. So the evaluation of our model is very straightforward. We just have to invoke evaluate on the test set, which has these test vectors and these target values. Okay, so now there is some error here. Yes, because I forgot the comma separating. Yes, okay. So one thing that you may want to do here is to print out the test loss. And the test accuracy. Okay, so that would give you an evaluation of the neural network computed on unseen examples of the test set. Okay, what else? Next, you may want to save your network. So let's create another section here for saving our neural network for later use or deployment to production. So this is very straightforward as well. We get our trained model and then we save it to whatever path. So let's call this artificial neural network path. This is where we save our model. And okay, before I forget, I will give a value to this path, So it might be something like, I don't know, like home, natural, BP, whatever, feed forward, network, and the extension would be HDF5, which is the format in which the network is saved. I forgot the equals sign here. Okay, good. Yes, and finally we can print a message indicating end of execution. That would be the end of the program. Yes. So now I am switching off this presentation mode. Okay. Let's have in our view the project. Yes. Let's have a quick look to our code. I don't see any errors. Let me check. Okay. Now we can go to our console. And okay, we can try to execute our program that will read the data set, and then it will create the topology, configure the machine learning, start the training, perform the testing, saving the network. So that would be the whole process. So this would be it. The dataset may take a while to load because there are hundreds of thousands of instances in the dataset. So this may take a while. This is the version of Tensorflow 2.1.0, and now okay, we may have an error here. Let's see. We forgot to define something. Train, test, split. Oh yes, I see what happened. I forgot to import that, so we can import it right away. So from this is in scikit-learn model selection. and we have to import the train test split. Okay, I think we are ready to go. Import. Let me see if we have any problem here. We may have some invalid syntax. Yes, I don't know why this is not complete. So the class wait function. Okay, now it should be ready to go. Let's check. Okay, so this is it. Now you will be seeing from epoch number 1 to epoch number 1000 the training of your network. This is going to take a while, so at the end you will be able to see the quality metrics of the neural network computed on the test set. So I hope this was useful to you. If you want to provide any comments, please feel free to get in touch with me. You can find me by email or in LinkedIn. My name is Ignacio Giraldez, and I hope that this was useful to you. See you on the next one.